primarily to motivate the use of Gaussian processes. And what I said was, again, to summarize that part of module 2. So what the reason why we spent so much time in this module to talk about Gaussian processes was that when we will come back to Bayesian filtering, we would like to avoid to use or to make the assumption that we know the functions that model the state transition, or to model the functions that will that tell us how the state processes map to observations. So we will then have to, on the top of estimating the latent processes, we also have to estimate functions. But now, and then the role of the Gaussian processes was as a tool to estimate these functions. And what is more, we also introduced a Fourier-based Gaussian processes, where we create features for these Gaussian processes, and then we end up to estimate linear parameters that will be very, very convenient when we come back to the problem of sequential estimation of latent processes. But now, what about these deep Gaussian processes? So one limitation one can argue about Gaussian processes is that they really require that we have this assumption of joint Gaussianity, which in some cases is not really appropriate. And what deep Gaussian processes then offer is a solution that basically allows to model any kind of relationships. And this is kind of similar to what you have seen is, for those of you who have followed the literature on neural networks, to create actually deep neural networks. And what that means is to keep stacking elements that would, in our case, would be Gaussian processes. So it is, in fact, the idea to stack a number of Gaussian processes and allow the input of the next, let's call it Gaussian process, to be the output of the previous Gaussian process. And this is how it is. So let us assume, in this case, what you see, X1 is actually an observed input. In what we will see later in module 3, we even do not observe X1. But let us assume that X1 is an observed input, and then this input is producing X2. Before, X2 was Y, so X1 directly goes to Y. And the function was modeled by a Gaussian process. This arrow is the function. So now you have X1, and there is a function. Let's call it F1, and it produces X2. This is what you see with the first equation. So this arrow is a function that maps X1 to X2. And now this X2 is an input for the next function, F2, and it produces X3, and so on. So here you have FL such functions. So before we only had one function, now we have more than one function. So if you have more than one function, then you have a deep Gaussian process. So each of these functions now is modeled by a Gaussian process. And this composition that is written at the bottom, where Y is represented as a function of only X1, is a deep Gaussian process. So the concept is very, very simple. Of course, it's not trivial to find the unknowns of the deep Gaussian process, but it is somewhat simple. And this is exactly the same philosophy that is being used in deep neural networks. So here is an example of just a deep Gaussian process with two Gaussian processes. F1 and F2 are modeled as Gaussian processes. So what is the generative process? You generate, so you have X1. From X1, you use the function F1 and you generate X2. And you can add also some perturbation, which is given by this other term, sigma 1 epsilon n x. And then finally, you obtain y n here as F2, another Gaussian function that comes along the Gaussian process that takes X2 in, and we have some other observation. So again, F1 and F2 are these latent mappings that are unknown, and we modeled as GPs. So here I on purpose used a subscript n because in machine learning, n would be an n, maybe nth patient, for instance, or nth observation. So I'll get back to latent processes and observations in module 3. So this is the generative process, and this is how these actually these functions may look like. For instance, what you see on the left is a nice smooth output where x1 is on the x-axis and x2 is the y-axis. This is the left plot, so it's pretty smooth. And then when you put it through another GP, what you get on the right. It's very, very nonlinear, and now obviously when you had some observations y and some inputs x, so you have input-output relationships, then the objective is how to find these functions f1 and f2, so that once you train these functions, once you estimate these functions, then you can readily obtain for any new input x a new output y. So if it's regression, obviously, if it's classification, you'll then classify that x into something that it. This is an example of, and then the inference. So how do we actually find these functions f1 and f2, and how do you find x2? So on the top of having to find f1 and f2, we also have to find x2. So x1 in this case and y are observed. So so the learning requires maximization of this log marginal likelihood that is you see here. So x2 is actually integrated out. So it is, you can argue this is like the evidence function, and this is actually the approach. So one optimizes the parameters of the Gaussian process using the evidence, and then one also can estimate x2 in the usual way when we deal with the latent variables. And just some final remarks about deep Gaussian processes and deep neural networks. One thing that is interesting that has been shown is that if you take a single layer, so one Gaussian process, or maybe when you take a single layer of fully connected neural network with an independent and identically distributed prior over its parameters, and with an infinite width is equivalent to a Gaussian process. So you know that neural networks are composed of layers. So if the number of the width of that layer is infinite, then this is equivalent to a Gaussian process. This was shown by Redford Neal. Then one can argue that deep Gaussian processes are equivalent to neural networks with multiple and infinitely wide hidden layers. So every layer is infinitely wide. This is when you have radial basis functions. So what is different between Gaussian processes and deep neural networks or neural networks is that neural networks introduce nonlinearities of all kinds, ReLU and so on, whereas the Gaussian processes don't do that. So so these nonlinearities are basically implicit in the Gaussian processes. They don't need activation functions. That's one difference. So one thing that I mentioned and that is not so present in not present basically in deep neural networks is that we don't have knowledge of how the uncertainties propagate as you go from layer to layer. And with deep Gaussian processes, you can follow how this uncertainties Then there is also a possibility to allow for automated relevance determination in each layer of the structure. And just to not to advertise, but simply to mention some of my current work with some other students is related to how to use Gaussian processes to determine causation. So that is an important problem, and it's not trivial at all, because even scientists and philosophers cannot agree what causation is. But let us assume that we assume causation in a mechanistic way. It's not like what is called Granger way. And Granger way would be the rooster is not the cause of sunrise, because you notice that, well, after every, when the rooster is awake and is out there announcing the new day, then there's sunrise. So you might think, well, maybe it's the rooster that causes the sunrise, but it's not. It's just has predictive power. That's what Granger is. So this is also part of our work, in which way actually some signals can be used to predict other signals. Now, what is important here is that we don't know the functions. So we don't know how some input signals can be used to predict some output signals. And what we do is we use Gaussian processes. And not only that, but also using Gaussian processes, we can measure how important some of these signals are for the prediction. So we can even attribute so much is this signal important, so much is that signal important, and so on. What is more, we also can attribute uncertainties. So if you're uncertain about the prediction of particular signal, say Y, then and it has 5 inputs, then you can say it's uncertain. Part of the uncertainty comes from X1, part from X2, part from X3, and so on. And one can also extrapolate this for using deep Gaussian processes. Okay, so now I'm switch. Any questions about this? So now there's one more short review that I want to do because this will be part of our model using deep state-space models. Something that some of you may be very familiar with, some of you may know it a little bit. It has to do with linear regression. And the reason I want to mention this is because we deal with problems where some of the unknowns in our models are also static parameters. And then, and it's again something that I think all of us who deal with Bayesian filtering should be very familiar with. So let us assume that we have this model y equal to phi transpose theta plus epsilon, and phi is this known feature vector. So phi is known feature vector, and this feature vector it's not shown here. The elements of phi are actually a function of the input vector x. So phi transpose theta is what we might call the signal part. What is not known is theta. Theta is the unknown parameter, and epsilon is Gaussian noise with unknown sigma squared and with 0 mean. But sigma squared is not known. So what is not known is sigma squared and theta. So what we would like to do is to find the joint posterior of theta and sigma squared. So this is joint posterior formed after observing the data from time instant 1 to time instant t. So we are back to our time notation. And also we would be interested in finding yt plus 1 given y1 to 2. So what is very convenient often in Bayesian analysis is to use conjugate priors. What that means is you assume a prior, and then what you get is posterior that is of the same belong to the same family as the prior. So what we do here is we assume that theta and sigma squared have a multivariate normal inverted gamma distribution. And it is given, the form is given on the screen. And this distribution has several parameters that have to be adopted. A0, B0, which are have to satisfy these constraints. And theta 0 is also something that has to be assumed, as well as the matrix sigma 0. So so this is something that something that you have to assume, and these are what are called the parameters. You have to start with something. Obviously, you can assume priors for these and go in the levels, but it has been shown in general in theory that this is fine. One can start with this, and very soon the data will overtake what you assumed. So again, we want to find the posterior of the vector theta and the variance sigma squared, and we start with the prior. So now, when we look at with this prior, when we look at the predicted distribution of y given phi, the feature vector, and these hyperparameters A0, B0, sigma 0, what we really obtain is that this y has a PDF that is the student's t distribution. So this is something that will be again important, and I'll mention it again. So what we found is that what one can find is that this predicted distribution. So remember, we still have not used y to find the posterior of theta and sigma squared. We just say that if you choose this prior, then the predictive, the first sample that you would get should come from this distribution, from the distribution. And these are the parameters that are given one, phi 1, and sigma 1. For those of you who want to find a derivation of this, can consult this book by Zellner. So now we come back to the posterior. So now you observe y. So the predicted distribution of student t. Now you observe y, and then you want to find what the joint posterior of theta and sigma squared is. And the answer is it's again a multivariate normal inverse gamma, but with different parameters. So that's the beautiful thing. So basically, you started with normal inverse gamma. You use your y to update theta and sigma squared, the PDF of the joint PDF of theta and sigma squared, and you find that it is going to be, again, multivariate normal inverse gamma. And you can see here, so A0 became A1 with this update. B1 was obtained from B0 with this update. And you have the first estimate of theta 1 hat. It's updated from theta 0 using this equation. All right, so this is the first part that I would like to mention. Before I actually move to particle filtering, my version much briefer. We had Denise's presentation today. So what I will say now is that now if you want to predict y2, given y1 and all this, you'll get another student distribution. And then the updated joint PDF of theta and sigma squared will be another normal inverse gamma PDF with new sets of parameters, A2, B2, and theta 2 hat. This is again the beauty of the Bayesian methodology. It is very harmonious, and especially in this kind of settings, when you choose carefully your priors, then the rest is like beautiful music. It just keeps going. And so let's talk about particle filtering briefly. Now I will mention the things that are of interest to what I will explain next. So so one thing that is of importance in many signal processing problems is, again, tracking these hidden states that I mentioned already. And again, I repeat here, we have the transition PDF and selected with x3 as the other equation. And so here yt is a scalar and xt is a vector process. And what is important is, in particle filtering is that one of the densities that we want to estimate are this part is filtering density, and to obtain this filtering density from the previous filtering density. So the filtering density at time instant t from the filtering density at time instant t minus 1. One thing that when I was starting working on particle filtering, one thing that attracted me to particle filtering was its generality, in the sense that first of all, it can be used for any type of transition PDFs and any types of light. So this was something that well, not many methods can afford. Now, true, it is can be computationally expensive, but it can really be applied to a large number of much wider number of problems. So as Dennis showed this morning, particle filters approximate the PDFs of just three measures. So and then what we actually have at every time instant, the support of the state at time instant t is represented by the particles that were drawn for that particular state. And this is another way using Dirac delta functions to represent the filtering density that is here represented with m samples, and then xt minus 1 superscript m represents m particles of xt minus 1, and delta 3 is the Dirac delta function, m is the number of particles. So here they represented with equal weights. So, and the process is kind of straightforward. I think it's my understanding Victor will provide tomorrow a more general description of what you see now on the screen. So the standard description goes like this. So you are now at time instant t minus 1. You can think of these xt minus 1 n to be a member of the what we might call the mth stream. So there are capital M streams of particles, and then you draw xtm first from ext given xt minus 1 m. Obviously, this is only one version of this. One can have different proposal function than p. So I use the bootstrap version of particle filter to show here. And then we have this computation of weights, which is given by the second step. So here you compute the likelihood of xtm given the observation yt. So these weights sum up to 1. And then now we have this approximation that you see as the last equation on this screen. So every particle is accompanied with a weight. And then the last step is resampling of the particles. So basically what you do is you want to typically start with a new set of particles. Some of them will be replicated, but particles that are not very hopeful to be good particles will not be used from then on. Now this has some ramifications. I'm sure that some of other speakers will talk more about this. But resampling is something that we have to do with particle filtering for this bootstrap version of particle filtering. So here is again the problem that arises if you do not do resampling. So what you see here at the bottom is some particles shown here in yellow with yellow circles, and these particles were, say, sampled from some important sampling function, and then one evaluates the weights of these particles, and weights are here shown with basically with the radius of these purple circles. So this particle here, for instance, here is going to have the largest value. This one here will have a small value. And your set of particles and their weights you represent your filtering PDF. And then you go to the next time instant. You didn't do any resampling, and these are your particles. And then roughly, so not probably I should not suggest this graph should not suggest that the text did not change its value, but suppose that it didn't change much. And you can see how this actually value here, and also the distribution has not changed much from sample to sample, how this particle here gained so much in weight that all the other particles became negligible. And you don't want to approximate your distribution with just one particle and the rest being negligible. So this is a problem, and this is corrected with something that is resampling, and this is again a graph that shows how this is done. So practically, you see on the left here again particles with different weights. So the larger the circle, the larger the weight. And then if one say decides to split the interval into equal subintervals, and then see how much space each of these particles occupy, you can see how much they, on average, would be replicated. So this particle here will be replicated. So there, instead of one, now we have three same versions of the particle. This survived, this did not survive, the yellow survived, and the purple did not survive. So this is the operation of resampling and some of you who are more familiar with particle filtering know that there are many ways of doing resampling, not only one. But my experience is that whichever way you use, you will not see much difference. The only possibility that it's worth looking into these different ways of doing resampling is by finding out which are faster than others. So the speed is important sometimes in sequential. And then this is the pictorial description of particle filtering when you implement resampling. So again, at the bottom, we start at the bottom, and all these particles are of equal weight. Then the second set of circles show the same particles, but now weighted. So some are weighted more, some are less. And then from each of these, you can see we have children. So this largest circle has generated 3 children. Some have no children at all, and some have 1 children. And then these are propagated further, and you can see now these 3 particles here have larger weights again, because they come from part of the likelihood that is have larger values. And you can see now how actually in the part of the space of X where you have more probability mass, you have more particles. And that's actually the idea. So, and those parts that are not so important basically remain very sparse with particles. Okay, so this was not yet. So this is actually what I wanted to say about particle filtering. So the generic algorithm goes like this. You start with some set of m particles, x0m, that are drawn from the prior, px of 0. And then they are assigned equal weights, 1 over m. And then we propagate the particles according to some PDF that in the case of bootstrap particle filter, it's basically the transition PDF. And then we compute the non-normalized weights of the particles, and then we normalize them. Then we have also resampling, which is which should be mentioned here, but it's not. I think it's left below. So this was particle filtering. So the reason I mentioned particle filtering is because we will use it in the remaining part of the module. And we will use the Gaussian processes, and we will use also Bayesian linear regression. 3 things: Bayesian linear regression, Gaussian processes, and particle filtering. So we go back to our standard phase model, which is given by this set of expressions. So here we assume that the noise vectors ut and vt are Gaussian, and we also assume that they are zero mean. And what is very important now, the functions f and g are not known. This is different. So then, what we do is we make now this jump from this model, and we say that, well, we will represent these functions from the previous slide here to these functions, where you can see now we have x of t, which is represented as a product of a matrix h of t of size so h is of size 2 jx dx, and theta here is another matrix of size 2jy times dy. Px and phy are feature vectors. So let me explain this a little bit in more detail. So these ph's, px and phy, are constructed in the same way as I explained before with when I talked about random Fourier-based Gaussian processes. So so H transpose is the transpose of this matrix. So H transpose in the first row has eta 1. Eta 1 becomes now a row vector, and eta 1 is that static parameter vector. And you're multiplying this feature vector phi. It's multiplying this feature vector phi. The size of the feature vector phi is 2jx. Jx, remember, is the number of sampling, the number of frequency vectors that we sample from the power spectral density of the current. So I repeat, phi represents is that feature vector with cosine, sine, cosine, sine, cosine, sine. Cosine, inside cosine we have x transposed times omega vector. This omega vector is the first vector that we sample from the kernel. Then you have sine of the same thing. Then cosine with the second vector, omega 2. Sine, same thing. So these are, given x, these are known. So phi of x, phi minus 1, is assumed to be known. And what is not known is h. So now we have this H transpose matrix that has so H transpose has dx rows, and each row corresponds to the value of the state vector x1, x2, x3, x dx. So x1 t is this eta 1 transpose that multiplies phi. Then we go to the second element, x2 t is now eta 2. It's a different parameter vector multiplying the same feature vector, and so on. You go through all these different. I said I would not write on the board, but let me just repeat here. So you have this x1 p. This is the first element. So it will be eta 1 transposed. This is phi of, say, x of t minus 1. And you have plus this noise here. Now x2t, we have another vector, but it's the same phi, xt minus 1, plus and so on until we hit dx. Dx transpose phi xt minus 1. So each of these elements have their own parameters that one needs to estimate with time. So for now, we keep these parameters eta 1, eta 2, eta dx to be constant. But as you can now anticipate, there is no reason to keep them constant if you feel that actually the model changes with time. So we can also make eta to be a function. And now we can add, maybe I can talk this at the end, you can add another set of equations that model how eta changes with time. So one simple model would be the random walk model. And then guess what? You have, given xt, you have Kalman filtering for the etas as they change with time. But let's get back to this. I will talk about this possibility. I'm sure I'll have time at the end. So what you saw here for h, the same thing applies for theta. And px and py are constructed in the same way. And these etas and thetas are initialized by Gaussian pairs. So now guess also what? So now we have so many equations. So this one is one equation where you have to estimate linear parameters, and you have noise variance here that also needs to be estimated. So for this, because you have linear model with unknown variance, you have the Bayesian linear regression that I mentioned earlier. So you use the Bayesian linear regression to find the joint posterior of eta and sigma squared. And but this is only for the linear part. This is assuming that you know x. So coming back to the model, what are the unknowns? The unknowns are, of course, the vector process. This is the unknown of primary importance. And then the parameter matrices h and theta, and the noise variances sigma u squared and sigma v squared. So here we will assume that each of these noises here that are added, they have their own variances, and we estimate them separately. So that actually multivariate Gaussian is with covariance matrix that is diagonal, but with different elements along the different values along the diagonal. So what is the strategy again for estimation? So we still resort to particle filtering to estimate the latent states of x. So given the estimated states, we update the joint distribution of h and sigma and theta sigma u and theta sigma v. So once we estimate the states, we switch to estimating the h and sigma v and sigma u and sigma and then theta and sigma v. And as I said, for these updates, we use Bayesian linear regression. And I just briefly explained earlier how this is done on a very simple example. So we get estimates of all these matrices, also theta, and also the variances of the noises. So what is the procedure? We propagate xt. And then when we propagate xt's, now we have available xt's. And from these xt's, we construct these features. They're all now given. Then, given the features, we can update the thetas and the variances and the etas and the variances. And then we can compute the weights of the particles and estimate xt. So So what is interesting here is the following. I also mentioned this earlier. So when you propagate XT, we would need in general, let's take a look at this. So when you propagate XT, we would need knowledge of these variances of UT for every U, U1T, U2T, U3T, and so on, UDXT. But we said that we do not know them. We can estimate them, but we do not know. Of course, one approach is use the last estimate of these variances and then propagate. But what we do instead is let us not use estimates, but simply integrate out these variances. And then when you integrate them out, and I show this, you get student distribution. So for propagation of states, we use student tree distribution. But this is something that at least in what you'll see some results of what we do later. This is what we have done. So the updating of the joint posteriors of eta and sigma u squared and eta sigma v squared, we again apply the Bayesian linear regression formula. So it goes, it's like ping pong. So first you propagate using the student t distribution. So then what we have is we propagated the particles. Now we compute the joint posteriors of these unknowns here in the eta matrix and the theta matrix. And then with this, we can compute the weights of the particles. Once we have the weights of the particles, we can do estimates of the state. And then we can do resampling, obviously. And then we go back and propagate for the next time instant. So there is something else that we have also tried here and that we can do. And this is what we call ensemble learning. So as you know, we often, first of all, it's a model, what we have used. And this model is a model that is based on all kinds of assumptions, for example, that the noise is Gaussian in the state and solution equations. But also, in our case, we have assumed that the Gaussian processes have certain types of kernel functions. So, for example, we said that the kernel functions was a function that was exponential squared. And then this function may have certain parameters, and you saw how these actually have different features. So what we can actually do now is we can assume that we have maybe Gaussian processes with different functions, and we run them in parallel. So what that means is you choose your favorite kernel function, and then you draw frequencies from the power spectral density of that function. That's GP1, Gaussian process 1. Then you can repeat the same thing for Gaussian process 2, Gaussian process 3, and so on. So you have as many of those as you wish, and they all run in parallel. And then you implement the same thing for each of these GPs. And then at the end, you want to combine the results of each of these GPs. Now, this is fusion. And then some of you who have worked on fusion, you know that there are also various ways of doing this fusion, not only one way. But the point here is, though, that now we use not only one GP, but ensemble of GPs. So now here is what we denote with kappa S is basically a dictionary of kernels. And then we create a set omega S by sampling from the power spectral density of each kernel candidate, kappa S. And then we assign to, but so this is also kind of interesting as well. So we have weights for the particles in each of these filtering schemes, but also now we can assign weights to each of these actually members of the ensemble. So some GPs would be better than others, and then you're given weights, and these weights are actually proportional to the quality of the GP based on the data up to time is completion. And this is how this is one way of combining. So basically, what we're doing is we're saying that the ensemble estimate of XT is given by a mixture where each mixture is weighted by a weight WTS. So one thing that, I mean, there was earlier a question about identifiability. I have to say here one important thing. So, so the estimates of the latent states by random feature-based models are identifiable up to a scale, shift, and rotation. So scale, shift, and rotation, but one can actually, let's say, correct these in a principled way so that they can be, let's call it, aligned, and only after that we can combine them. Otherwise, you'll get garbage. All right, so now I switch to deep state space models. So this is a diagram that shows what a deep state space model is, and a deep state space model with L layers. So let me describe it. So you have the first layer, and the first layer is what we would call a standard process in the sense that it is Markovian. So you have the state x1 at time instant t-1, and then it moves on to become state x1t, and then state x1t plus 1, and so on. So this state x1 t-1 is in general of low dimension. So low dimension. And this then state is projected to states of higher dimensions. So let us say this is of dimension 2, the next one could be dimension 10, this could be dimension 50, and then you have finally your observation process y t-1, which can also be high dimensional. So so you start with low dimensional states, and then you increase the states as you progress from lower layer to higher layer, to a higher layer. So then the task is even more complicated in the sense that not only that you have to estimate, for example, this lowest level process, but also all these intermediates. And then, as you can now anticipate, when you go from a lower level to a high level, there is some mapping. And this mapping is done using, again, Gaussian processes. I mean, these mappings are modeled. The functions that you want to estimate are modeled by Gaussian processes. So every arrow is a Gaussian process. Even these arrows are Gaussian processes. So you basically have to estimate the GPs, all the arrows, and to estimate all these axes that are in the on this graph. Not only that, there are also other unknowns. As you saw, we also have variances that have to be estimated, and because these GPs contain these linear matrices with linear parameters, they too have to be estimated. So lots of unknowns to be estimated, and I will show how we do it here using just, it's fairly straightforward extension to what I showed so far. So let me summarize again. We have all these processes on every layer to be estimated, and then each of these processes are combined, or rather met via Gaussian processes as functions that are modeled by Gaussian processes. Each of these functions have their own sets of unknowns that need to be estimated. Now we can ask the question, why actually are we doing this? What do we gain by modeling observations using these deep state-based models? One area is actually coming from neuroscience. So many studies have shown that that actually the way our brain works is sort of similar to what is shown on this diagram. So there are, so these are representations that are particularly useful when you have the following. When y is high dimensional, and then x is low dimensional, and then typically it is not a good idea to go from a high dimension immediately to a low dimension, but you do it gradually in steps. So then you have much more ability to do things with these intermediate processes that are being modeled here. So again, according to neuroscientists, the way how our brain is constructed, we have layers of neurons, and then each of them have their own processes that are taking place, and they're all connected. So things don't work in one layer only. And as you all know, the reason why we live now in the era of re-emergence of AI and machine learning is simply because deep neural networks were reinvented. I remember when I was, when most of you were not maybe even born, I remember I was attending, as assistant professor, I was attending a conference in San Diego, California, and it was maybe 93 or so. And then there was a panel on of these funding agencies, and I, as professor, wanted to hear what kind of research they would support. And the first speaker came on the stage and said, "Please do not send any research proposals on neural networks. We will not accept it. We will not fund it." This is how bad the situation was. So much was promised and not much was delivered. And then 10 years or so passed, and suddenly things exploded again. And people figured out how to actually optimize these neural networks with more layers. All the networks that were studied until that time were very shallow. So there were no these intermediate layers that I'm trying to explain here. So yes, the depth plays a role. And again, this allows for lots of flexibility in modeling processes. So what is now the mathematical description of what you saw on the previous slide? Let's go through this. So let's start with the last equation. Oops, the last equation actually shows this observation process. And as you see, it has the same form as the previous equation with only one state process. So you have this theta matrix that multiplies phi ty. And phi ty is a function of the last process. This is the only process that y sees. Y is connected. So this is phi ty that is constructed from from x capital L t. This is the last latent process, and with of course with its own variances of nodes. So this is the last equation. But then each of these other equations that connect, say, the process before that is above xl t minus 1, so xl minus 1 t minus 1, is modeled by this equation. So it has its own H matrix and its own feature vector. And again, the feature vector has to be obtained from the state process above. So the kind of the parent process. So if you think of this, if here we have xl minus 1, t minus 1, this will be a parent process to this process. This is the child process. And so each of these will have similar representation like here. And we finally have the last one, the first one rather. And this is the process with what I would call with the lowest dimension. And it is in fact a process that is Markovian. So here one uses the process before. So this is a child of the previous value of the same process. So again, there is one equation here for this arrow. There's another equation here for modeling this process and this process and this process until you hit this process. And for this process, you have these arrows. So you can see all the functions that are not known are modeled by GPs. Each GP has its own parameters that have to be estimated. and they have their own variance that also have to be estimated. These parameters and variances are also estimated by using Bayesian linear regression. And the rest, one applies particle filtering for the rest. So it's a combination of particle filtering and Bayesian linear regression. So here's the inference. So there is one thing that I don't like, and that remains to be researched. And this thing that I don't like is we have to predefine the dimensions of each of these intermediate processes, of all the processes, basically. So here I'm still thinking about problems that exist in neuroscience. So in neuroscience, as I mentioned earlier, you observe a multivariate time series that can be very high dimensional. And then you would like to model this multivariate time series using this deep state-based model. Now, what I don't like is I have to say to the model what the dimension of this process is, the first process, then the next one, the next one, and the next one. Now, obviously, one can start testing different models with different dimensions, but if you have even four such intermediate processes, that can be a lot of, it will quickly explode. There has to be a better way to finding these dimensions. And this is one direction of work that we are focused on, how to determine these dimensions. So we assume the dimensions for now are predefined. And the objective is to estimate the latent processes, all the latent processes, and all the parameters of the model H and theta. Now, what is interesting is, and something that I did not mention, you can say, I asked, why do we need to do this? Because it's very complicated, and why do you need to go so much in between processes? So, as you know, those of you who read papers in neuroscience, many of these processes cannot be interpreted. However, what one can see is, when I say cannot be interpreted, the values cannot be interpreted. But what one can see is the following. So you have a high dimensional process, YT, and then you do this analysis, you go and you start tracking. And then you can see, people have done experiments with, for example, animals or even with patients, that when there's a change in behavior, there is a change also in the, you cannot see it easily in the Y process that you observe, but you can easily see in the low dimensional process. So there is something into what I would call all these important things are really living in these low dimensional manifolds. So yes, it looks a very high dimensional process, but what is interesting is lies in a very low dimensional. So not only that this can be used for the, and I'll mention this also at the end, and if I have time, I'll elaborate a little more, is that one can also do with this type of modeling a regime change, detection of regime changes. And as you can easily imagine, when you study this kind of time series, multivariate time series that are high dimensional, then it may not only be important to find how the states change, but also if there are any particular big changes due to certain interventions, for example. So this can only be done, obviously, if you have a good model and if you can accurately estimate these parameters of the model, in particular in the matrices H and theta. And there there's one H matrix, but there are L such matrices theta. So if I have only until 5:30?
5:30.
Okay, so what are the steps? So, all right, so what we do is we, in fact, work with particles for every state process. Why do we work with particles? Because remember this equation. These models are very nonlinear in X, and so we use the particles for estimating the state processes. So once we have the values of X, we can update the joint posteriors of all these linear parameters and variances, and then we compute the weights of the particles, and then we estimate the latent processes. So what I would like to show here are some examples, some experiments in fact, if you're interested to read more about this, this is a paper that shows some of these results. Some of you who would like to get the code, Yuhao, I think he has made his code public, but if you have problems to find it, let me know, and you can try this code. So here's one example. So it's a simple example in the sense we only have, so here's the case where we do not have deep states process, simple space model, where the dimension of X is 2 and Y is a scalar. And what is more is, so the state equations for X1 and X2 follow this expression. And you can see they are very intricate, and we assume that we did not know them. So this is how the data were generated. The data were generated like this. First state process X1, the first of the two state processes, that the state process was two-dimensional, was the first equation, and the second was the second equation. So this is what we used for the state processes, and the observation process was generated by using this equation. Again, it's very, you would never try to estimate, even if we had, it would be very challenging to estimate if you knew exactly the form without knowing the parameters, for instance. So we assumed we did not know this equation, and this equation. And the data contained, so this series had 2,000 samples. And what was done was, so the first 1,000 samples were used for training the model. And in this experiments, we used only 50 frequencies, both for X and for Y. So only 50 frequencies. And so what you see here is results of the first process. So the red line shows the actual value of the process, and the estimated latent process was in blue, and this kind of blue, not gray area, shows the uncertainty about the latent process. So what you also notice is that this is something that you probably have seen this in your courses in estimation theory. So where do you see that uncertainty is the largest in the estimation? It's where in this case, almost like a sine is changing its value, it reaches its peak. And it is the least uncertain, or the estimates are the best, is when the function crosses 0. And this is not so strange. And if you look at Camara bounds, for example, you will see the same thing. When the function is changing the most slowly, is the worst place to estimate, and where it is the fastest changing, it is the best place to estimate. And this shows up here without. So this gives me confidence that these results make sense. So, but what you see on this plot is the second dimension of the latent process. So again, the actual latent process is in red, and what you see in black are different realizations. So what was done, what they did, what Yu Hao and Marge did was they would start the estimation with some training, and then continued the estimates, and then you get one black curve, and then you restart it again, and then they got a different estimate. So you can see how actually these estimates vary from realization to realization. So this is done with 20 runs from different seeds. So so this plot here shows pairs of estimated XT and actual XT. So the red dots are the actual latent states, and black dots represent the estimated states. So what I said, one has to be careful in how to sort out the estimates because of the identifiability problem. So what is typically done in these cases is to use single value decomposition. So with single value decomposition, you rotate and rescale your estimates, and then they will then match very well to the estimated states will match very well the latent states. So this is an example with the case when now y is 100-dimensional. We had 5-dimensional state. So there are 5 different state processes, but y is 100-dimensional. And so I'm not sure if you can see here, but there should be 2 lines. One is the red line, and this is the actual latent process. And with the black line, you can see the estimated process. And obviously, how well these aligned depends also on the parameters used in the estimation. But even when it is even high signal-to-noise ratio, you could argue this is pretty challenging problem. Remember, you don't know anything about the functions, and yet you're still able to capture these processes. So in each of these, yeah, you can see this. So there is, of course, discrepancies, but for most of the time, it looks like the estimates are following the true values of the state processes. So here is one more attempt to argue for the need for the models. And in fact, I'll show you one example. So it is true that before you start working on a very challenging problem to decide, is this really something that is important? Would I spend precious time research on something that nobody cares about? And let's see if this makes sense. I will show you one example. So what we did was we did an experiment where the true state space was 10-dimensional. So dx was 10, and y was only 1-dimensional. And then we generated the observation process as a GP, whose kernel was a superposition of a dot product and a Mattern kernel. So this is one type of kernels. And also keep in mind that the dot product kernel is a non-stationary kernel. So here are the results of the simulation. So this is root mean square error plotted. So on the y-axis, the root mean square error. And this is a time on the x-axis, and you can see how the root mean square error was a function of time. This is per sample, and what the red curve shows is when you had one hidden layer, and you can see that in one hidden layer, you actually it was doing so poorly that the root mean square was increasing now with time. You could not track. Now with 2 or more layers, things would improve with time. And in this case, the best performance was shown with this green curve, which is the 2 hidden layer Gaussian process state space model. So this is what I said. So how many layers to use can be done, I guess, using experiments like this. Try different number of layers and then experiment. But then in true in real world settings, things can be further complicated. One can even argue maybe the number of layers can also change with time because for some processes, if they change the structure, that may require different architecture of the deep Gaussian process. So this example again should, I can use this example to argue that yes, deep state-space models actually make sense. And then some more results that show the performance of the deep state-space model. So here we have two hidden layers. The first layer, so this is the one that is at the top, had two state processes. So this is the first one on the top. And these are the equations that govern how x1t and x1t1 and x1t2 vary with time. And the second layer had three processes. So we have two processes on the top, three processes and again, I keep reminding you that these functions that were used to generate x1t and x2t are not known. We don't know them. And this is a four-dimensional observation process, and you can see that this again process has very many functions of the input of the variables, and as you can see, they're all coming from the second set of processes, x2t. So again, I repeat, these are not known. And these 5 plots show how we estimate these processes. So on the left are the two, in red, the two processes that are on the top. And with red is the true values, and on the with black are the estimated values. Now, of course, there are things that are not good, like here, but most of it, the process seems to be staying with the red curve. And these are estimates of the second processes, one that are actually used to map to obtain that the observations y. So again, these results give us hope that using this methodology, one can indeed reveal not only one state process that is directly connected to the observations, but deeper in the architecture of the state space model. And I would like to summarize this with the following statements. So the first is that deep Gaussian processes implemented by fully random features at high capacity for learning deep state space models. And one example was, I showed one example where we saw that a shallow state space model was not good enough. So what is also important is the methodology for estimating all these unknowns is fairly straightforward because it is based on just two methods. One is the particle filter, and the other one is the Bayesian linear regression. Then, as I said earlier, these models can be extended to include time-varying linear parameters. So these are the linear parameters used for the Gaussian processes. So then one would have to implement, rather than Bayesian linear regression, Kalman filtering with particles. They keep. One can also maybe use, even within one step, maybe a couple of iterations that might improve things. I mentioned also that with the Kalman filters, one can track these parameters theta if they smoothly change with time. But also one can implement this methodology to find switching regimes. So models with switching regimes would be models as follows. So you have in fact, this is something that we have also already been worked on with the same team. So what it means is the following. So let's make it simple. You have one state process, X of t, but this state process is operating in kind of quasi-stationary mode in a particular time period. It operates with one set of parameters, for instance, and then it suddenly switches to something else. And then again, it stays there for a little time. We don't know when it will switch. It will switch again to something else and something else. So you can argue this is kind of a classification / estimation problem. What you're classifying is to find a class to which particular regime belongs to, and then of course to estimate the process itself. So again, one can use on the top of the assumption that you have GPs, I can use other models on how, for example, how long you expect that the particular regime will last. For instance, one could use what is known as, I'm not trying to drop names, like Yule-Simon processes. Yule-Simon processes are processes that model staying in the regime in a way that the longer you are in the regime, the more likely is that you will stay in the regime. It's like the rich get richer paradigm. So, for instance, one can use that, if that makes sense, of course, for your problem, to use that also as part of your model, and then you have to estimate also that Yule-Simon process. So, but coming back to what we're talking here is that very important is that these parameters of the GPs can also be time varying. And it's not a big deal for us because then we just apply the Kalman filter rather than Bayesian regression. One nice thing is replaced by another nice thing. So, and the last comment here is there are interesting venues for research that include determining the structures of the deep state space models. So the number of layers and the dimension of each layer. So yes, this is something that is also of interest. In fact, one can do, if one wants to complicate things, can in fact do even something more complicated, and which is the following. So you have your observation process here sitting, and then you have these ensembles of what I discussed already, and then this ensemble of Gaussian processes is fed by a different ensemble of Gaussian processes that is sitting in front. Then you go deeper and deeper. So this actually very much resembles deep neural networks. That's how they look like, more or less. And again, there the problem is, as is also for deep neural networks, is how to find the architecture. Which architecture would be the best for? So obviously, one can do model comparisons, but that's not, that's pretty linear approach. There has to be something cleverer than that, that one could maybe use to, with more training to, as done in evolution, like with particle filtering, go in this direction, add a layer here, or add another set of GPs to improve the learning capacity of and the predictive capacity of the model. So I will stop here. I will just leave maybe some time for questions. If not, I would like to talk a little more